So first off is to come up and speak is a bioengineering professor. Bioengineering, so it's going to be it's a different background, which is nice. Not everyone's computer science and math. This bioengineering professor at Stanford, previously physics at Berkeley. And so if I had to bet on who in this building has the strongest natural understanding of how the universe works, I would wager it is this person. Now they're starting a company that's focused on robotics. They're going to build an AI architecture for smart, safe, governable robots at OpenMind. I'm excited to introduce Jan Liphardt.
Okay, thank you so much for that introduction. Also, thank you to the organizers for organizing this kind of event, which is useful for all of us. In terms of understanding the world, unfortunately, I have to defer on that. But based on many years of teaching physics for pre-meds, I definitely know how to wake up 300 students in a lecture hall. So today, I'd like to tell you about some work we've been doing primarily in robotics. And here we go. So the implications of large language models, when you ask people, okay, what are these things good for? Typically you hear things like, my students say, oh, I can do my homework. My children say that too. We can replace lawyers. We can generate beautiful ads and videos. And those are sort of generic use cases for large language models. But much more broadly, the technology has implications for robotics, implications for science, implications for defense, and implications for organizations. You can imagine in a few years from now, organizations that have computers in the middle and humans at the periphery, as opposed to the geometries we have today, where we have humans in the middle that may be using computers. The central premise of everything we do at OpenMind is that current LLMs naturally speak robot out of the box. And this is true for basically all models today, O1, Claude, Gemini, DeepSeek. They all already speak robot out of the box, but most people don't know this. What you have to do is you have to take an output from the large language model and you have to convert it into something that you can send to a hardware abstraction layer. You can do this in any number of ways, through custom grammars or through prompts and so forth. So be advised that the next time you use a large language model, it is very straightforward to connect that to robot hardware. The way we think about these kind of systems is that the LLM is like a blind, deaf person. And so imagine having a relative that's blind and deaf, and your goal is, as you traverse the world, is to narrate the world to them using natural language so that they know what's going on. And then in response to those natural language inputs, they can perform actions like walk, not bump into things, pick things up, live their lives, eat, and interact with others. So from a robotics perspective, a large language model is very similar to a blind and deaf person. In terms of the architecture for the open source software that we're building, this will be released on February 1. And one of the reasons we're at this event at Democratizing Intelligence is that we want to democratize smart robots. That's why we're open sourcing everything, and that's why we write technical reports that describe what we're doing, and we just put them online. So we kind of care about this, and we definitely want to make it broadly accessible. In terms of the basic software architecture, it's sort of as you might imagine. We have a variety of sensors, and how on earth do I go back? Apparently, I don't go back. Huh? Oh, it did it. Splendid. Let's try it here. So we have a bunch of inputs, vision, sound, hardware, location, LiDAR. Each one of those data inputs feeds into a model that converts those data into natural language, English sentences. And then we fuse the English sentences into a paragraph, and then we send a paragraph to a large language model. And this is exactly analogous to helping a blind, deaf person navigate the world. A paragraph is all it takes, it turns out. That may be counterintuitive, but happy to dig into that assertion a little bit later. Once the data arrive and are fused, they go to the LLM. And then we have actions coming out. Typically, we use a combination of LLMs, like a supervisory LLM dealing with other agents. And out of the conversation arises actions. These can be things like moving. Sorry, this is very confusing to me at least. Here we go. Imagine working with the slowest computer you've ever worked with. There we go. So going to the hardware abstraction layer, we have things like movement, sound, speech, facial expressions, and other things. So that's roughly what the architecture is like. February 1, it will be all open source. You're encouraged to run this on your humanoids. You can run this on your quadrupeds. You can run this on your satellite in low Earth orbit, and you can run this on Turtlebot 3. It will also support Turtlebot 5. In case you were wondering about my assertion that a paragraph is all it takes, you all know this intuitively anyway, because if you have a blind and deaf relative, as you're traversing a school, room, university, as you're narrating the world with natural language, that relative of yours or a parent or child of yours is able to do amazing things with just natural language inputs. And as you know, the brain operates, the core part of the brain we care about operates at something like 40 bits per second, which is like Morse code. Some people have this perception of the brain as this like fully interconnected piece of magic. But the brain is actually a modular composite of processing nodes, and the core fusion operates at somewhere around 40 bit per second. Here's a technical report if you care about the details. So it's on the archive because we just open source things. And the slides probably will be available publicly as well, so in case you need the link. Here's an example of some of our quadrupeds running around the USS Hornet. And the quadrupeds are in fact running OM1, the software. So multiple inputs, converted to natural language, fused, go to LLM, generate hardware abstraction layer commands. So OM1 helps solve part of the problem, which is how do you make machines smart? But it doesn't solve a related problem, which is imagine us living in a world where we're surrounded by thinking machines. What does that mean for us people? I'm convinced, and perhaps you disagree with me, but I'm convinced that very soon, on timescales of 1 to 2 to 3 years, we will be surrounded by thinking machines that are smarter than most humans. And we can have a long conversation about whether you believe that, but if that were true, what kind of infrastructure would we like humans to be surrounded by? So let's do a thought experiment. Imagine for a moment you're a thinking machine that's smarter than humans. You have lots of problems. For example, you don't have a name. You don't have a passport, you don't have an eye fingerprint, you don't have a birthplace, and you don't have a birth date. So that means that a lot of infrastructure that has built for this implementation of thinking machines, which is a massively parallel wet electrochemical computer called the brain. So we built infrastructure that's very suited to ourselves, but a lot of this infrastructure we built is not well suited to other compute architectures. So in this thought experiment, what kind of infrastructure would you like or would be useful for you? We're spending a lot of time on using, as crazy as this sounds, and I apologize in advance, on using Ethereum to do that. And it is unfortunate that a lot of the use cases for blockchains have been, frankly speaking, incredibly underwhelming and dumb. But in this particular situation, in this particular problem statement, I think there is an exceptionally strong case to be made for needing a global, public, immutable ledger that is very good at storing things like strings and laws and rules and dealing with identity and things like that. So we've been spending quite a bit of time on connecting our operating system, OM1, to decentralized infrastructure for things like tasking, identity, and payments, and so forth. Where is this all going? Imagine a sort of new economy, sort of a generalization of the gig economy, where we're able to solve particular tasks with teams that are dynamically composed of humans and machines. This is relevant not only for manufacturing, but also something, for example, the military cares about a lot. I'd like to do a quick call out to two people in the room from Nethermind, and they're working on something that we think is incredibly interesting, and other people in this room may think is incredibly interesting too. That's the concept of a one-time model. So imagine a cryptographic sort of digital object that you can send per email, and the recipient is able to run that model once or n times. And that is a new way of thinking about how to share data and knowledge and skills from one machine to another and so forth. So just call out to our collaborators from Nethermind in the audience. In terms of why are we at democratizing, why are we at this meeting? Well, we think what we're doing is democratizing robot intelligence because we're creating these open source physical wrappers, physical embodiments for things like Claude, Gemini, and DeepSeek. And all of a sudden, you can now shake hands with DeepSeek or Gemini or Claude, and those models can explore the physical world, collect data, make decisions, and interact with people. Any questions? Jan, Paige, or Adam are at your beck and call. Thank you so much.
We'll open, as we've been doing, for questions for Jan. I think we still have the microphone. Oh, do we? We don't have the microphone. Let me grab a microphone. Oh, it's here. Cool. Right over here with Kader, for anyone who wants to ask questions to Jan. Thank you. Okay. Here you go.
Thank you.
Hey, Jan. Super cool presentation. I'm just curious if you've seen this. So, we've all seen really funny hallucinations from LLMs when you're doing some sort of chat-based thing. Do any weird hallucinations happen when you use LLMs to control a robot?
Oh, the craziest stuff happens. For example, we in our prompts, we say, if the LiDAR alerts you to a potential collision, we inject a sentence into the prompt that says, there's something dangerous on your left. And if we tell the LLM that it's a dog, guess what it does? It turns to the left. And we ask the LLM, hey man, we just told you there's something dangerous on your left. Why are you turning left? And the LLM told us, what do you mean? I'm trying to smell it. Because the LLM was completely convinced it was a dog. And the LLM told us, well, I'm a dog, and if you say it's dangerous, I don't know that. I'm going to smell it first. And so the way to debug our collision avoidance was to ask the software, like, hey man, what on earth are you doing? And then to realize that it is completely convinced it's a dog. And that means we have to write the prompts in the correct way. So there's been all these fun experiences when the other thing we've noticed, just fascinating, normally when you program robots, you do end-to-end AI. And then, you'd imagine you collect 10 million hours of YouTube videos on cats, 10 million hours for dogs, build 2 different end-to-end AIs. But in this kind of system, you can change a single word to change the dog into a cat. And so you can have a quadruped in front of you that thinks it's a dog. You can make a single word change to the prompt and say, hey man, you're a cat now. And then the quadruped now runs away from the other quadruped dogs because this one thinks it's a cat. And so there's 2 implications. One is a change of mindset for how you program robots. And the other is the great ease of reprogramming or retasking robots to go from cat to dog to board-certified radiologist by making very small changes to prompts. So we're basically living on the shoulders of Sam Altman because of all the data they have ingested and are contained in the large language models, which we can repurpose for robotics.
Sorry, one follow-up. So you literally, in your prompt for the 4-legged robot, you tell it it's a dog?
Absolutely. And again, February 1, it's all going to be out there.
Super cool. Thank you.
Thank you so much. Could you talk a little bit about the state of the industry in robotics? Specifically, which companies are maybe ahead of others? Is it like NVIDIA or Tesla with their robots, or maybe some Chinese companies? Or is it still very early days for everyone?
That's a long conversation. So there's software for robots and hardware for robots. China is very significantly ahead as it relates to hardware for robots. For example, the quadruped we buy, we pay like $10,000. Well, we pay like actually $3,000 each. And if we go to Boston Dynamics, it's 20x more expensive for similar performance. So from a hardware supply chain perspective for humanoid and quadruped, China is ahead. We're seeing very slowly hardware manufacturing in the US also spin up. Figure comes to mind first, obviously Optimus and others, 1X and Amazon and everything they're doing. So the hardware side is definitely gathering steam. It probably has not escaped your notice that OpenAI is spinning up a robotics team. And I guarantee you this is going to be a major trend across all like AI companies. It's going to become clear very quickly that a major unlock of the technology is for all of robotics. You can talk to the robot, almost immediate like retasking, repurposing, completely changes how it's thinking about the world, how it's aggregating data, and then making good decisions based on data that someone else has collected for you and condensed into the LLM.
Forgive me, I was just skimming through your paper that you had posted up there, and so I haven't had a chance to fully read it through. But I was wondering, why is it that you think that language is a good intermediate, let's say, structure for communication with robots? Because it seems to me that language is good for debuggability and human interpretability, but not necessarily the most efficient bandwidth for or mechanism for being able to go to all this inter-agent communication.
Well, you've already answered 70% of your own question by virtue of your 3 initial responses. Mm-hmm. With respect to your 4th response, I couldn't agree more. Mm-hmm. We should definitely anticipate thinking machines developing their own language, which is not necessarily optimized for communicating with humans. And we're already seeing that happen when different LLMs talk to other LLMs. Mm-hmm. They'll invent their own language. Mm-hmm. But I'm a strong proponent for building systems that I can peer into and have some possibility of figuring out what the heck is going on, mm-hmm. and having English sentences fly around that are interconnecting the entire system makes debugging almost trivial. So that's the main argument for why we use natural English language as the sort of data communications medium in the software.
And so as a quick follow-up to that, obviously, like a lot of people, including stuff that I do at my startup, we use prompting because it's very fast, it's iterable, but it's reasonably high cost once you end up specializing on a particular task, because these models are very general purpose and quite expensive. And so it's great you can flip from a dog to a cat, but the cost of doing so is perhaps high. Do you envision that this is kind of the early innings and that over time it'll end up going towards lower cost, more specialized, maybe less interpretable models?
That is a fascinating question. There's all sort of considerations about if you're building a defense robot, mm-hmm. you obviously want to do a lot of compute at the edge because of jamming. Mm-hmm. And so then you have a strong constraint operating on your operating system because it has to run locally. If you're in a if you're in an environment with good connectivity, then of course you can just hit various cloud endpoints. That's one stab at your question. And certainly if you have a Roomba, you want it to be very good at cleaning your house, and you presumably you can reduce cost by virtue of having a single-purpose system, mm-hmm.
Mm-hmm.
With reduced like compute needs. So I totally agree. Everything I just talked about has most benefit in the setting of like rapid reprogramming, for example, of a factory. Right? It's not going to be particularly useful for like a $35 like a toy dog that sits on your desk and can bark or something like that. You're better off just focusing on that one specific task.
Awesome. Thank you very much.
Thank you so much, Jan. Thank you.
Yeah, thank you so much, Jan.